Welcome to our binomial distribution question examples part 2. So here's a second question that'll lead us through some good typical binomial distribution questions. All right, so if we're going to tackle question A, just like everything else, we always have to identify, well, first of all, we should check and make sure that this is binomial, right? And it fits the rules of a binomial, that all the trials are independent, the probability is constant, and you only have two choices, two outcomes, and it fits all of those, right? The two outcomes in this case are, it results in a sale or it doesn't result in a sale. Everything's independent because it doesn't matter, if one um, website visitor has a sale or not, it's not going to influence whether the other one does. And so they all have a constant probability of 1 out of 1,000, right? And we have a set number of trials at 2,500. So it satisfies everything. We know it's binomial. So let's write down all of our information. N is our sample size of 2,500. P is the probability of what we're looking for. In this case, it's the probability of a sale, which is 1 in 1,000, which has a decimal, 0, 1, right? Tens, hundreds, thousands. That's 1,000th. Q, right? Obviously, if you're going to use the formulas, then Q is 0.999. We won't be using that for technology, but if you're going to do these things by hand with the formula, you're going to need that. And I showed you the formula in the first video. And then X, right? We got to figure out what our X is. Well, in the case of this one, they will have more than 5 sales. So X has to be strictly greater than 5. That's what we're looking for. But as you'll recall from the first video, most all of the technologies that we use do cumulative distribution functions, which means they start with the case where x is 0, and then they work up to and add x equals 0, x equals 1, x equals 2, 3, 4, all the way up to x equals whatever you set it to be. So if we want the cases of being bigger than 5, right, so 6 and above, we're going to have to set x equal to 5 in our cumulative distribution functions. It's going to count up all the 0 through 5 cases, and then we're going to subtract that from 1 to get the complement, because then that will give us the cases 6 and above. So just for, you got to kind of pay attention. If this had been 5 or more, then we would set our functions to 4 instead, right? So we would accumulate the cases 0 through 4, and then that would leave us with 5 or more. But since we don't want 5, right, we want strictly greater than 5, then we're going to put 5 into the function that we're going to run in SAS and Excel and so on and so forth, and then subtract that from 1, and that'll give us the answer we're looking for. So with that being said, let's do SAS first, right? So we go to our code, and we got to pick the right one. Remember, we set this up last time. We saved it so we can use it over and over again for outcomes for X or less, right? So 2,500, probability of 1. We would do 4 if we wanted 5 or more, but since we want strictly greater than 5, then we're going to accumulate everything up through 5, run that, and then here it is right here, the second one, 2,500, right? And then this is the probability here of 0 through 5, and then we want 1 minus that, right? So we would subtract that from 1, and we would get 0.0419, right, if we wanted to round. Okay, so that's how we would get it out of SAS. All right, how about if we were going to do it in Excel? Well, I've got my nice little easy binomial distribution spreadsheet set up in Excel, right, where we're using the binomial distribution function. And if you don't have the newer Excel functions, and you don't have the binomial distribution range function, then you're stuck with doing this and then kind of doing the one less than trick. But you would set up your number of successes. In this case, remember, we want the number of successes to be more than 5, right? So we set it up as 6, because more than X, right, is what we're looking for. Number of trials, 2,500. Probability, 0.001. and then this should be our probability. Sorry, I just brain farted. We want more than 5, obviously. And so 2,500, right? And so here's our probability, that 4% that we got from the other one, right? When we subtracted it from, well, we got the, the straightforward way. This is set up to already do the complement. If you have the binomial distribution range function, which is this one here, right? It gives you a range of numbers where the first number, C3, is your number of trials. The second number, C4, is your probability, right? And then the next number is where you start from and then where you finish. So in this case, we need to just type in, we want to go from 5 to 2,500. And that doesn't seem to be right at all. Did I not have the right probability in there? Duh, of course, I made the same stupid mistake again. And because we want greater than 5, we want from 6 to 2,500. So we had to make that 6 to 2,500 in our formula. And then that's how we would get it out of that one. And then, of course, in our calculator, second distribution, right, we've got to go down to the binomial, CDF, choose that, 2,500 trials, 001, right, is our probability. And again, this is the CDF that accumulates up to a certain point. Since we want greater than 5, then we want to stop at 5. Paste that. There's that 95%, that same thing we got out of SAS, and then we got to do 1 minus that to get the proper answer. Okay, so that's Part B is just reminding us again of what we need to have in order for binomial distributions to work, right? We need to assume that the internet hits are independent and that the probability of a sale basically remains constant. And we talked about that already. Now, if we want to move on and do part C, we have to use the Poisson approximation to compute the probability. Now, the formula for a Poisson population, and I apologize to any of my French subscribers for my horrible butchering of that word, um, but here is the formula. It's mu to the x times e to the negative mu all over x factorial. Now, E is, what we think of as E when we see it. It's the constant, right? That's the exponential number 2.71828, blah, 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 goes on and on and on forever, right? It's in all your calculators and all that kind of stuff. Mu is the mean number of occurrences of the event over the interval. So it's basically the mean of this situation. And remember, with binomials, the mean is really easy. The formula for a binomial is just n times p, which makes sense. Um, you know, n is how many trials you have, p is the probability of a success. So if you multiply those two together, that will give you the average number of successes. Think of something really simple like flipping a coin, getting tails is 50-50, right? So p would be 0.5 or half. If you flipped a coin 10 times, what would the average number of tails be? It would be 5, right? Now, that doesn't mean you would get 5 every time. It just means on average, that's what you would get, and that would be 10 times 0.5. So that's how the formula works. So in the case of this one, it's 2,500, right, times 0.001, and this equals 2.5. So that means if they get 2,500 hits per day, that's their time interval, then on average, they should expect to get 2.5 sales per day. Hopefully they're making a lot of money on those sales, because 2.5 sales per day is probably not going to keep the lights on, but that's what they're getting. Now, if we wanted to use the formula, just like with the binomial formula, you have to do them individually, right? So we would have to do um, the probability of 0 sales plus the probability of 1 plus the probability of 2, right? Plus the probability of 3. And we want for more than 5. So plus the probability of 4 plus the probability of 5. Get that number and then do 1 minus that answer, right? Because we need the complement, because this is the cases of 0 through 5, and we want more than 5, right? So we want 6 and above, just like from the previous example. But we don't want to have to run this formula 5 times, just like we didn't want to have to run the binomial formula 5 times. So luckily, we can do it in all 3 of our technologies. We'll start with SAS Studio. You'll see down here, I've got the code for one outcome, and it's just like before, it's a PDF, right? You'll notice kind of the similarities is your PDF is when you're doing one outcome, and then you just have binom in here for binomial. CDF is when it's cumulative, binom in here, right? And then you have, sorry, I keep going too far, PDF and then Poisson, CDF and Poisson. And then when you want to do normals, it's the same thing, CDF, and so on and so forth. I want to take a moment to point this out. You'll notice that this is in purple and this is not. I had all of this text in a Word document and I copied and pasted in here. And sometimes Word formats things differently, and it formatted those apostrophes as these weird apostrophes. Can you see the shape of these, how they're curled and these are straight? And so in SAS, this will not work. It doesn't see this properly because these symbols are wrong. You have to actually come in here and delete them and put in just the normal straight, and then now look, it's purple, and now it's going to work, right? So just something I wanted to point out because this happens a lot. If you find code online and you copy and paste it, oftentimes the the font that they're using will screw things up, and so just keep an eye on stuff like that. Anyways, we're doing the Poisson one, and we want it for the CDF, right, for X or less. And then I have here reminding myself that M is the mean and N is the number of interest. So in this case, remember our mean was 2.5, and our number of interest was 5, because we want to sum up the first 5 of those things. Okay, let's run this. And then down here, here is our Poisson probability. It's one of these two, I can't remember which, because I've got so much code going on there. But it doesn't matter because it's the same number. But you can see this would be for up to 5, and then we would do 1 minus that. We get like 4.2-ish% would be our answer. Now you remember from our previous calculations, the binomial, we got like 4.19%. This is like what, 4.02. It's or 4.202. So they're really close. I mean, they would both round to 4.2 if we rounded to one decimal. So they're very, very similar between the two, which is why we would answer, is it accurate? Yeah, it's pretty darn accurate. Okay, really quickly, let me show you how to do it in Excel. It's easy. It's the same thing as all of these things, right? Poisson distribution. If you double click on it, it tells you what you need. You need the variable of interest, which is X. You need the mean, which is 2.5. And then cumulative. Yes, you want cumulative. Once again, that's the probability of up through 5 equals 1 minus this, and then that as a percent, right? Give yourself a couple more decimals, and you can see there's that same answer of 4.2, very similar to what we got up there. In the calculator, right, we go into the same in our distribution menu, scroll down until you see there's the PDF, for that's a single, CDF, right, for the cumulative. I've already put in here, this means mean, so there's 2.5, my value, paste it, run it, and again, that's up through 5. We'd have to do 1 minus that. I like to just do this and then know that that's my answer, but positive. It's kind of a shortcut on the calculator. All right, so those are two basic examples of binomials, and we even ran one of Poisson. All right, thanks.